Good afternoon, everybody. Thank you so much for coming. This is the Advanced Services and Offerings track. Really appreciate you taking time out of your busy days to come join us today. This morning we had a presentation from Mike Kuntz on Route 53 and Virtual Private Cloud. Right now, Brian Tracy is going to give us a presentation on Amazon RDS and Aurora. And then Chad Schmutzer and Chris Malik will give us a presentation on ECS, and then I'll finish up CloudFormation. Hope you enjoy it. Stay for the whole track. Thank you so much.
Great. Thank you, Larry. Good afternoon, everybody. As Larry said, my name is Brian Tracy. I am a solutions architect with AWS. I cover the Southeast region for state and local government and mid-market education. I am going to try and prevent any of you from slipping into food coma, understanding that we just had lunch. My only thankful thought is that at least I'm not in the last session of the day between you and the drinks. Sorry, Larry. So as Larry mentioned, I'm here to talk to you about RDS. I come from a background of about 20 years of software development and leading software engineering teams and enterprise database administrators. And so today we'll do an overview of RDS and all of the different platforms that RDS offers, and then we'll take a little bit of a deeper look at Amazon Aurora. So first let's start with a poll, a show of hands, if you will. How many people are familiar with RDS and how it functions? Okay, so a fair amount of folks. Same raise of hands. How many folks have provisioned RDS workloads? Okay, a little bit less. Great. So for those who aren't aware of what RDS is, let's talk a little bit about that. RDS is a managed database platform. So what that means to you is you don't have to worry about provisioning a server. You don't have to worry about patching an operating system or loading database bits on top of it. You literally start with, hey, RDS service, I would like a database, and choose your flavor and a couple of other parameters and go from there. RDS comes in 6 familiar engines. Of course, Amazon Aurora that we'll talk about here last today, MariaDB, MySQL, Postgres, Microsoft SQL Server, and Oracle. And as I mentioned, it's as a managed service, a lot of the routine tasks that you would normally have to do when you're hosting your own on-premise server or database server are handled for you with the RDS service, and we'll dive deeper into what that means here in the next few slides. So why did we build Amazon RDS? Honestly, the biggest question, the biggest answer to that is customers asked us to provide a database service that was easy to use, was scalable, was secure, and operated at very high levels of performance. So again, and you've probably heard this earlier today, you heard Andy Jassy talk about it, 90% of AWS's roadmap in terms of services and offerings are driven by customer ask. So it's folks just like you saying, you know what I really need? I really need this. Managing relational databases is hard, as the slide says. Doing things like provisioning the environment, what I talked about earlier, establishing backup and restores, dealing with patching and things of that nature. Also achieving things like scalability and high performance are very difficult. Database tuning in your on-prem environment takes a skilled hand and is very difficult to achieve. So how does RDS compare to the traditional database hosting? So the column on the left is not exhaustive by any means, but shows you a lot of the details around particulars that you'd have to manage and deal with and plan for when you're talking about hosting your database in your on-prem environment. So first you've got to purchase that hardware, right? And you heard Mr. Jassy this morning talk about a 10 to 18 week procurement timeline. In some cases that could be longer. I worked in government contracting for a while, and that procurement cycle was much longer than that. Then you have to do things like load the OS. If you're going to create a clustered database, you have to load your clustering software and get all of that configured and working properly. Then load your database bits on top of that, and so on and so forth. With RDS, as I mentioned earlier, you start by saying, hey, I would like a database of XYZ flavor. Here's about how big I want it to be. And from that point forward, you really focus on what's important to your business, and that is optimizing your query logic and making sure your applications are performing at the anticipated level that you need to service your customers. All of the other maintenance tasks but below those covers are handled by RDS, and again, we'll talk about that here in a couple seconds. So it's easy and fast to deploy. In order to get a production-ready database, you can literally do this in a couple of minutes' time. As I mentioned, there's a couple of fields that it will ask you to provision, i.e., what flavor of database do you want to run, how much compute do you want on your database, meaning number of cores, amount of memory that you want your database to run. In this case, you see things up here like the licensing model. Some of our databases, which aren't open source, come in either a license included or a bring your own license model. You have varied versions of the database engine, so we have a pretty good offering of the different versions of a particular database engine. Down there, that shows you about the instance sizing. Multi-AZ, we're going to talk about more in another slide or two here, but that essentially gives you a primary node with failover capability. And then your storage type and how much storage you want. Finally, you'll get to some configuration around how much do you want to persist to backup. With RDS, they're automated backups that we call snapshots. They are incrementals that act like fulls. So every day when your backup runs, you're not having to back up hundreds of gigabytes or terabytes. It's essentially doing the diffs or the incremental from the last backup. However, they perform like fulls, which is pretty nice, and they give you full point-in-time recovery. The enhanced monitoring is a newer capability that allows you to not only select that you want enhanced monitoring on your database, but also specify the particular granularity in terms of how often do you want these metrics persisted, right? In this case, I chose every 60 seconds, but you can get down essentially to about every second. And then, of course, the maintenance window. RDS will apply minor database patches for you, and you can either choose, as with the backup cycle, you can choose the existing sort of predefined Amazon window for doing this maintenance or your backups, or you can define your own maintenance period to do those backups. This slide just shows a simple application architecture. It is not highly available, just to be clear, so this is not exactly a best practice, but it gives you a pretty good idea of a simple architecture that you can run on AWS. In a couple slides here, we're going to see the more elaborate architecture that is employing things like best practices. In this one, you'll see an elastic load balancer at the top. And even though this particular workload, this application server or web server happens to be a singular server, a best practice is to put it behind an elastic load balancer for a couple of reasons. One, so that your application doesn't have to experience an outage later when you choose to scale out and add additional servers beyond that. And also, the elastic load balancing service only supports TCP and HTTP. And what that means to you is it eliminates and doesn't even entertain UDP packet requests, and that isolates you from about the 85 to 90% of script kiddies out there who are screwing around on the internet and trying to do DDoS attacks on you. This thing keeps moving forward, and I think that's because I'm hitting the button. So I apologize. So you get down to the second layer here, which is your application stack. That could be a web server, it could be an application server, and then finally that's looking to a database behind the scenes. In today's discussion, that's an RDS database server. It could very easily be any flavor of database that you choose to run on EC2 instances. And then finally, S3 is in the picture here with the red bucket, and that's where your snapshots, which are your daily backups, are persisted to. So deja vu, you guys have already seen this slide. Multi-AZ, so what is multi-AZ? Clustering databases to give you a primary node and a secondary or failover node is very complex to manage. Even as a software developer or an engineer for 20 years, I never liked to put my hands in that batter, right? And I had a very good friend who was an enterprise DBA at my last company, and still, I left it up to him, and it was still sort of voodoo to me. Multi-AZ option within AWS takes a lot of that voodoo out of the equation for you. It's literally as easy as saying, yes, I want the ability to have a primary node and a failover node in another availability zone, hence the reason we call it multi-AZ. And that insulates me, from a total system failure, right? If my primary node fails in under 2 minutes, the CNAME will be switched from my primary instance and will fail over to my secondary instance. When that happens, an additional secondary instance is automatically provisioned for you to make sure you continue to have high availability, right? Should that other node fail. It's physically distinct, as I just talked about, being in a separate AZ. The database is synchronously mirrored, so you can be sure of atomic writes. So when your data is written to the primary node, that data is synchronously written to the secondary or failover node, which of course helps you in terms of no data loss when there's an issue. I talked about failover occurring automatically in response to scenarios where something might fail. And then something that I haven't mentioned yet, which was the planned maintenance. So when you're running in multi-AZ mode, the maintenance is actually performed on the secondary node first. And then once that maintenance is completed on the secondary node, the system will actually fail over to the other node, and it'll patch what was the primary node but is now the secondary node. What that means for you is a minimal amount of read-only time that your database is experiencing when that patching occurs, right? So we do everything to ensure or assist that your infrastructure and your applications are up. So here's that secondary slide that I talked about. It's a little bit more of a resilient architecture. In this case, we've chosen to take that application tier or web tier and load balance that. It may be also using a service like Elastic or auto-scaling rather to be able to scale your EC2 instances up or down to match your workload. They're reaching back to what you see below as the master node or primary node, and then you see the secondary node off to the right where the synchronous replication is happening for your data. And then, as always, the S3 is holding your database snapshots for your data persistence and backups. RDS comes with a few different flavors of storage to help you, again, not pay for something that you don't want. There's 3 different levels of storage that RDS offers today. There's a general purpose storage, which is an SSD-based storage, a solid-state backed storage solution. That's burstable, so it provides anywhere from 3 IOPS per second to 3,000. It can burst to 3,000. Provisioned IOPS is where you define how many IOs per second you want your database to perform at. And the provisioned IOPS storage is a persistent and sustainable IOPS for that storage layer. So what that means is it will be within 10% of that IOP rate for 99.9% of the data storage lifecycle. And the provisioned IOPS is meant for really high I/O workloads, right? Where general purpose storage may be for medium-sized workloads or databases that have moderate I/O. Provisioned IOPS is really for heavy OLTP databases that are really getting hit pretty hard. And then finally, there's magnetic. That's for smaller workloads or databases that get hit very infrequently. Honestly, as an SA, my guidance to customers is there's so little cost difference between the magnetic and the general purpose SSD. I sort of say start at the general purpose SSD, and we'll investigate pricing later. And if that's still too high, we can move down to the magnetic. So one thing about databases is scaling can be difficult, right? Because databases can only scale so large, and typically databases are on a single system or they're a clustered set of databases, but you can only scale to the extent that you have hardware, meaning CPU and memory, to allow you to scale to, right? And at some point, you're limited in your ability to scale beyond that. What read replicas allow you to do is essentially have read-only copies of your database running on additional hardware that allow you to scale out horizontally for your reads. So in a scenario like that, you would still keep your primary database for the writes, because it would be the master, but you can have your application reach out and scale out to additional, I didn't even touch the button that time. You can even have it scale out to other databases for read, so you can spread your reads out, and that allows you to scale your database out and accommodate your traffic a little bit easier. Now I'm touching the button. There we go. RDS provides all kinds of security. We have things like, you guys are laughing at me. We have things like SOC 1, 2, and 3, PCI. These icons are pretty small, so I apologize for that. But things like ISO 27001 and ITAR. We also have capabilities built into RDS that you may already be familiar with from our EC2 side or our Elastic Cloud Compute side, called security groups. Those are stateful firewalls that allow you to control the ingress and egress traffic to your database instance. We also allow you to operate your RDS in your VPC. Your stateful firewalls will allow you to determine whether that traffic can leave your VPC. If you want to entertain traffic on your RDS tier from your on-prem, for instance, or, and I'm not saying you should do this, or if you opened your database up to the outside world, which I can't imagine one good use case why you'd want to do that, except maybe you were a government agency offering up a honeypot to try and catch criminals. Identity and access management is built in as well, so you can provide fine-grained access and control to your RDS databases. So if you have particular members of your organization that should be in there, administering and configuring that environment for you, great. If you have users that maybe you want to be able to provide a read-only level of access, you can do that. And AWS's identity and access management allows you to apply those fine-grained controls to that database tier. We also offer encryption both at rest and in transit. So you can be assured that your data will be safe while it's down on disk or while your particular application or web tiers are reaching back to your data instance. CloudWatch is another Amazon service that integrates well with RDS and most of the other AWS services. It's a fantastic tool to allow you to be able to monitor the metrics of your database. You can monitor things like here it says CPU utilization, storage, IOs per second, memory, and things of that nature. You can also set alarms. So if your particular application experiences problems above a certain threshold, you can create alarms within CloudWatch and be notified of that so that you can take action if that particular case comes up. RDS is cost effective, so the whole idea of the cloud is to only pay for the resources that you're using and not to over provision, right? And so the idea here is only provision the database instance size that you need, and if you happen to outgrow that later, we can resize that database and enlarge it to run your workload as it changes. In this particular use case, I used an M4 extra large running MySQL in our Northern Virginia region. I did it as a single AZ and using the on-demand price. And we assumed in this case that a month was about 720 hours. So that particular instance costs 35 cents per hour to run, and with 100 gigabytes of storage for the database at 11.5 cents an hour, to run that for the month costs you about $263. So it's really very affordable to run that. Going a step further, all right? Another way that you can take advantage of AWS services but secure a lower price than our on-demand price is by utilizing something that we call reserved instances. And reserved instances essentially is making a commitment to AWS that you're going to run a particular workload for a year or 3 years. There we go. And the idea here is the on-demand price, as its name suggests, is on demand. So I can spin up a database today. I can run it for 2 hours, and then I can turn it off and never pay another dime for that database. However, the on-demand price is also the highest price that you'll pay as an AWS customer. So if you know you're going to run workloads continuously over a period of time, be it a 1-year or a 3-year period, you can make a commitment to AWS to say, hey, I'm going to run this workload continually, and I'm making that commitment, so I'd like a lower price, please. And reserved instances allow you to do that. So in this example, and I know that the eye chart's kind of hard to read, but the top line shows the on-demand price, and because it's an on-demand price, you're not paying anything up front, and so you're essentially, your cumulative cost or your cumulative spend is essentially $263.50 every month, right? With the 1-year reserved instance, you make an upfront payment, and then you'll see your cumulative spend goes up in very small increments month over month, and that's for the variable costs of things like the database storage and the IOs. So somewhere between month 7 and month 8, you'll start to recognize considerable savings, and by the end of month 12, you'll see that you've saved more than $1,200 over the cost of that instance using reserved instances. So how do RDS backups work? Again, we call them snapshots. There are automated backups, but you can also take manual snapshots. They provide a point-in-time recovery for you that's usually as early as about 5 minutes ago. And they're enabled by default, and you can choose between 0 and 35 days for your retention period of those backups. As I mentioned earlier, they're incrementals, but they act like fulls. So the backups themselves happen very quickly every night. You can also take manual snapshots, and there are good reasons and cases where you might want to do that. For instance, you're about to perform a very big upgrade on your environment. Please take a manual snapshot. Don't rely just on the automated nightly snapshots. Another reason I really like the manual snapshots is because if you happen to delete your database, all of the automated backups that were captured during the lifespan of that database go with that deletion, where the manual snapshots will persist until you choose to delete them. This thing is definitely wonky. Oh, there we go. We have an ability to allow cross-region snapshots, so this is really good in terms of a DR pattern, or also helpful if you're trying to migrate your data. It allows you essentially to say, hey, my database, I've got these snapshots here, and I want to send those over to another region as a DR pattern where I might want to have a warm standby of my database persisted. Excuse me. Or I may want to migrate my database to another region, and a very easy way to do that is to migrate that snapshot over to that other region and create a new database from that snapshot. It's very easy to migrate into RDS with the release of our data migration service tool that you heard Andy talk about earlier today, and the use of another tool called our schema conversion tool. You can easily migrate your database and its schema into RDS. What's really neat about the data migration service, so you can see down here at the bottom, or you could have seen, and this thing's really wonky, is not only would allow you to do homogeneous migrations, meaning if I'm going to go from Oracle to Oracle or SQL Server to SQL Server, but it'll also allow you to do heterogeneous migrations. So, and if you're running one of those very large enterprise databases that Andy talked about earlier, but you're tired of being held hostage for the cost of that, you can use something like data migration service and the schema migration tool to migrate out of that very expensive enterprise database and onto something like Amazon Aurora that we're going to talk here in the second part of my deck very easily and very cost effectively, and effectively see about 5 times the performance over MySQL and about 1/10 the cost. Excuse me. So why should you use RDS? Excuse me. For all those things that I talked about earlier, you don't want to manage things like migration, backup and recovery, configuration, patching, software upgrades. Oh, thanks, Larry. Excuse me, I caught a cold on the way up here. And And you really want to focus on things like the database schema, the query design, and the query optimization. Focus on your business, what's important to your customers, and don't have to deal with all of the other things necessary to operate a typical conventional database on-prem. So Amazon Aurora. This is part of the RDS offering. I'm super excited to talk to you guys about this today because of some of the things that Andy said earlier. Much like RDS and how customers asked us to provide a platform that will make it easy for them to operate databases, Amazon Aurora was a big ask from our customers who were tired of being held hostage by very large database providers and paying all that money for that performance and scalability. What is Amazon Aurora? So it's essentially MySQL 5.6 compatible, but what we did was, and we'll talk about this more on later slides, is we completely customized the storage layer in Amazon Aurora. So you get the performance and availability of those commercial databases, and you get the simplicity of operating an RDS database, and because it's delivered as a managed service, you don't have to worry about all of the very complex underpinnings of that database. So this slide really represents some of the changes that we made for Aurora. We reimagined it for the cloud. We took that logging and storage layer out of a conventional database where you would have primary nodes that would have their own storage, and then a secondary node would have its own isolated storage. I've got a better slide here that'll illustrate that. You guys are getting ahead of me again. It leverages a lot of the existing Amazon services, which are also built for high availability and performance, like VPC and DynamoDB and Simple Workflow. And it maintains compatibility with MySQL 5.6. So if you're running MySQL 5.6 today, you should have absolutely no problem migrating to Amazon Aurora. This chart shows you the performance enhancements. It's about 5 times faster than RDS MySQL. So the blue lines are Aurora, and the red and the green lines are MySQL 5.6 and 5.7. And you see almost exactly a 5x performance difference in throughput based on the MySQL Sysbench results. These results, by the way, are completely repeatable. We have a white paper on this that will allow you to provision your environments the way we provision them for the test and perform them on your own. I really like these slides because what these slides show you is how performance scales when you scale the Amazon Aurora instances. What you see below, you saw below, that the red and the green lines again are 5.6 and 5.7, and even as your instances go up and you scale to some very large instances, you'll see that your performance doesn't really scale with those instances, and that's not exactly what you would expect, right? The blue line that's up and to the right there on both charts, write and read performance, is Aurora. So you can see as you scale your instance types, your performance is going to scale greatly with the Aurora solution. Here's a real-life example of performance differences with Aurora. This was a gaming workload, and in this one, we're running an R34XL in a multi-AZ configuration. And you'll see that the left side is before the Aurora migration, and you saw the web transaction response time was about 15 milliseconds. And then after the migration to Aurora, it came down to about 5.5 milliseconds. So how did we achieve this? Essentially, there's not a lot of magic. We're doing less work, and we're more efficient. So we're doing fewer IOs. We're going to talk about that here in the next slide. We're minimizing network traffic and offloading some of the work that the database engine does. Almost all of the steps are now asynchronous versus numerous synchronous process steps in the traditional MySQL model, and we've reduced latency. As this slide says, databases are all about I/O. Network attached storage is all about packets per second, and high throughput processing doesn't really work well with context switches. So this is what a traffic pattern looks like in a typical MySQL environment, where in the second column on the right here is a read replica. And each one of those colored arrows, as the bottom will indicate for you, represents a different data flow, a different write, if you will. And you can see that you're making a lot of repetitive writes, not only to your primary tier, where you've got your primary instance and you're persisting it down to your elastic block store, and then you're doing a secondary write so that you avoid things like torn writes. But then you're going to replicate all that over to your replica instance, and it's going to do the same thing on its own storage tier. So you can see that the amount of traffic that you're pushing through that is considerable. So at the end of the day, that supported about 7.4 million IOs per million transactions, or about 7.4 IOs per transaction. Again, this is done with Sysbench, and this is repeatable. So let's look at what the traffic looks like in Aurora. So you see considerably less writing going on here. However, there's a couple things definitely worth mentioning here. So we're boxcarring all the redo logs, right? And it's ordered by the log sequence number. And so up at the top there, with the purple, which you can barely see, and the green lines, you're essentially pushing your redos over to your replica instances. But because Aurora uses a shared storage layer, they're all using the same underlying storage layer. So you don't have to replicate all of that data to n number of nodes with their own vertical storage attached to them, their own private storage. But what we do in Aurora is we replicate it 6 times across 3 different AZs. So you have an incredible amount of data durability. So we have 6 times more log writes, as you see down here in the bottom, because we're writing your data, essentially 6 copies of your data out. But 9 times less network traffic, because we're not doing all of those things that the previous slide was doing. You're not doing all of this stuff. And then, of course, it's all persisted down to S3. Aurora is automatically backed up and continually backed up to S3. So in the end, you see about 950,000 IOs per million transactions. So, and by the way, that accounts for the 6x amplification of storage, and 7.7 times less in terms of the IO performance from the other, and then 35x more of the actual transactions per second. Another thing that you see when you talk about having replicas is a separation, or what they call lag, between your primary instance and your secondary instance. And that's because that replication is typically being done asynchronously. And if there is enough lag or network weather, for lack of a better term, your asynchronous pushes to your replica may take time to get there, and they may take time to process. And then, as you may know, if your replica gets too far out of sync with your master, then you have some problems to deal with, and typically that meant you had to kill off your replica and recreate it. So replica lag is a really important thing to watch. With Aurora, because you saw we were utilizing the same storage tier for all of your nodes underneath the covers, replica lag is typically something less than 20 milliseconds. And in fact, in this example from GoGuardian, they saw replica lags almost in the 12-minute range, just using regular RDS with MySQL. And when they utilized Amazon Aurora, their replica lags never went beyond 20 milliseconds, even across 4 read replicas. So that's a pretty incredible stat. So here's what the I/O traffic looks like in Aurora replicas versus MySQL. This is another interesting slide that I really like, because when you think about scaling the performance of your database, you think about, as I talked about earlier, hey, my primary instance is really getting up there in terms of capacity. I need to create a read replica. And so you think, hey, if I create a read replica, I'm going to get double the performance, theoretically, right? Not so much. On the left here, this is what read scaling looks like in MySQL, in traditional MySQL. You're still having to write all of the updates in that one really noisy chart that I showed you over to your replica. So it's still handling 70% of the writes, just like it is in your primary node. So when you create a read replica, you're really only getting a 30% bump in your new reads for the capacity that it can handle. It's not really a very efficient model. And by the way, you're paying for a whole nother data volume and separate data storage for that. So it's not very efficient. With Aurora, again, because you're using that shared storage layer, essentially, and the only thing you're writing to your read replica is essentially your cache. And so if you've got pages in cache from your database, it will utilize that cache and update them. If those pages aren't in cache, it just ignores the page cache that's written to it because it can pull it from disk. So you get effectively 100% new read capacity just by creating that Aurora replica. So that really makes this model very scalable in the Aurora world. So this is a pretty profound statement. Performance only matters if your database is up. I like that quote, so I threw it in there. So let's talk about storage durability of your database. Amazon Aurora functions a lot like S3 from a storage capacity. So if you're familiar with the concept of S3 being an object storage where you can put as little as a 1K file and effectively store as much data as you want up to a single 5 terabyte file, Amazon Aurora works in a similar fashion. The minimum database size is 10 gigs, so it's not a 1K file, but you start with a 10 gig file and it will grow as it needs to on its own, so you don't have to provision the storage for it, and you don't have to worry about is my disk filling up and what happens if that does. And it will grow to 64 terabytes in size today. And it does that in 10 gigabyte chunks. We have a quorum system for read and writes. So as you saw earlier, I have 6 different data stores across 3 availability zones. For write consistency, we make sure that we have acknowledgement from at least 4 of those volumes before we accept that a write was successful, and 3 of those data volumes for read consistency. As I mentioned earlier, we continually back up to S3, and we utilize we utilize a gossip protocol to fill in the blanks. So earlier I mentioned that a lot of the data replication across these different storage layers is now asynchronous, and you may be thinking to yourself, well, when he said asynchronous as it applies to read replicas, that caused drift, and that's a bad thing. In this case, that gives you quite a bit of performance, but because we use the quorum method for 4 different volumes for writing and 3 different volumes for reads, that gives you the data resiliency, and then we use the gossip protocol to fill in the blanks so that we can ensure you don't lose any data. As we do with many of our other AWS services, we continually monitor things like the nodes for failure and repair them unbeknownst to you. The underlying disk, that's also monitored and repaired. I mentioned earlier that each of these storage segments is 10 gigabytes, and that was done in a very meaningful way because when you talk about having to recover from a database failure, the size of storage that you have to recover can be a pretty big deal. If it's a very large database and you have to go back and restore 4 terabytes of database, your restoration period is going to take some time to complete, to say nothing of rewarming the cache on that database. So we actively set each storage volume in an Aurora database at 10 gigabytes. And we did that because you can restore 10 gigabytes very, very quickly. So if we have things like hotspots or a data volume that fails, we can stand up a new data volume and repair that 10 gigabyte volume very, very quickly with very minimal or no impact to your environment. This talks more about the fault-tolerant storage. We're saving 6 copies in 3 different availability zones. We already talked about the 4 of 6 for write quorum and 3 of 6 for read, and the peer-to-peer, the gossip protocol for replicating repairs. The last bullet talks more about, because even if you have a 64 terabyte Aurora database, you essentially have thousands of 10 gigabyte volumes attached to that, powering that, and that's part of that model that allows you to spread your data out across numerous volumes, make it small enough so that we can quickly recover from a failure, and also give you the performance that you're looking for from the database. Another thing that we did, aside from changing the storage layer the way we did, was we removed the cache from the database, and we make that part of that 10 gig volume. So again, if you have a particular volume failure, and you'll see this on the next slide, your cache remains warm because it's no longer directly associated with your database. So one of the big things when you recover from a database failure is rewarming your cache, right? Bringing all of the data that was in cache back into memory, and that can be a very time-consuming process. And depending on your particular workload, doing that alone could also cause another failure. So we chose to remove the cache from the data volume, from the database layer itself, and handle it separately. So when you have failures in the database, your cache is still in memory and stays warm, shortening your recovery cycle. This talks about Aurora replicas for failover targets. You can define things like the failover order. It makes it real easy for rebalancing across Aurora. I didn't mention this earlier, but you can have up to 15 read replicas of Aurora, so you can really scale out horizontally for your reads. As I mentioned, the failing database nodes are automatically detected and replaced, and data processing will continue. A lot of vendors talk about, and particularly solutions architects, so I'm guilty of this, talk about planning for failure. It's really important for you to plan for failure, because if you don't, then you're not sure how your environment is going to operate when failure actually happens. You'll also hear a lot of vendors, thanks Larry. You'll also hear a lot of vendors talk about how their systems are, built for failure and very resilient. I like the fact that Amazon takes this a step further and builds in ways for you to simulate failures to see how this environment's going to operate when something bad happens, right? And so you can do things like fail a component in the database, or simulate the failure of disks, and for how long, right, and the number of disks, and simulate network failures. And so that will allow you to not guess at how your system is going to perform when a failure happens, but know how your system is going to perform when a failure happens. I already mentioned this, but Amazon Aurora is based on MySQL 5.6, so it's totally compatible with MySQL 5.6. Just that storage layer and the caching underneath is customized or proprietary. I say completely compatible with MySQL 5.6. There are some caveats. That assumes that you're using the InnoDB engine, of course. But all of your existing tools will work with the Amazon Aurora tool. So if you're using things like Tableau or Looker or Informatica or Slalom on your MySQL environments today, they'll continue to work with your Amazon Aurora. Here's many other third-party monitoring tools that I just figured be neat to show you that just because we're calling it Amazon Aurora, there is definitely some Amazon magic to it under the covers, but it is a MySQL compatible product. Migrating to Aurora, very easy, particularly if you're already running a MySQL database in RDS. There's literally an option to click on your database and say, hey, migrate my last snapshot over to Aurora, and it will literally go and do that in a matter of minutes. Here you're picking your database instance class, meaning your amount of compute power, and you'll select a couple other options for where you want it to run in your environment, and it'll be off to the races. So why Aurora? If the rest of my pitch didn't do it for you, it's architected for 4 nines of availability. It gives you that enterprise performance, 5x over MySQL at 1/10 the cost of some of those larger vendors. It'll automatically grow to 64T, so you don't have to worry about provisioning storage that you think you're going to grow into and you may never grow into. And conversely, you don't have to worry about, oh God, do I have enough database storage? Will I be able to do I have to monitor that, so I have to enlarge my database volumes later? Easy migration from MySQL, 15 read replicas is great. Cross-region replicas even better. Encryption in transit at rest, continually backup, and the best point of it all is that it's fully managed for you. This slide, I just wanted to show you some of the recent releases. My original intent here was to show you all of the releases in RDS over the past year, and I realized very quickly that would be an impossible chart to show you because it would just be a screen of little white dots. So this is literally just in the last 2 months or so of the different changes for Amazon RDS. You probably already know this, but like many of the AWS services, you can try it for free. If you just go to aws.amazon.com/free, you get a certain number of instance hours and can go out and try these things for yourself. I thank you very much for your time. I have 50 seconds left, so that is pretty good. In the interest of keeping Larry's track going, I will remove myself from the stage, but if anybody has questions or wants to talk more about it, I'll be in the back or out in the hallway. Thank you.